Again, welcome to Calculus. In these lectures, we will cover the continuity concept in functions. So our main objective is to determine the continuity of a functions. Also, we are going to determine the continuity of a functions on a closed interval. Also, we're going to use the greatest integer function to model and also solve a real-life problems. So we know in mathematics, the term continuous has much to do as the same meaning as everyday concept of using the term continuous. So in mathematics, the term continuous is much the same meaning as it has in everyday use. And when we say something is continuous, it means there's no stoppage. So from A to B, I continue doing something without stopping. The same concept apply here. So to say that a function is continuous at s equal to c means that there's no interruption in the graph when s equal to c. So this is unbroken at c. The graph also have no O's or jumps or gaps. So again, if we say that a function is continuous at s equal to c, means at the point x equal to c, the function is continuous. There's no breaking. So as simple as this concept may seem, its precise definition eluded mathematicians for many years. In fact, it was not until the early 1800s that a precise definition was finally developed. So before looking at this definition, we should consider the following function whose graph is shown below. So when we look at this graph, we have a graph that the interval starts from A to B. We see a closed interval from A to B. But from A to B, we can see that at point C1, there's a O. This means there's a discontinuous at C1. Same thing, C2, there's also discontinuous. At C3, there's also discontinuous. So F is not discontinuous. F is not discontinuous, only let's say from A to before C, C1. But F is not continuous at C1, at C2, and at C3. So here we also said S equal to C1 and F at C1 is not defined. From the graph, we can see that there's a hole between, broken. But at X equal to C2, S approaches C2, F at S, the limit does not exist. And also at S equal to C3, F at C3 is not equal to limit F at S as S approaches C3. So here we say that at all other points in the interval from A to B, the graph of F is uninterrupted, so it's continuous. It's only discontinuous at points C1, C2, C3. So the definition of continuity, here we say that let C be a number in the interval A and B. So within the interval from A to B, we have somewhere C. Now let F be a function whose domain contains the interval A to B. Now the function F is continuous at the point C when the following conditions are true. First, at point C, F at C is defined. Also, when S approaches C, the limit F at X exists. Also, when S approaches C, the limit F at S is equal to F at C. If these three conditions are true, then we say that F is continuous at every point in the interval A and B. Then F is continuous on the open interval A and B. Continuity of a polynomial function and rational function. A polynomial function is always continuous at every real number at F, so from negative infinity to positive infinity. And also a rational function is continuous at every number in its domain. What we mean by that is that a rational function can be a function with both numerator and denominator. So we know that if a denominator value is equal to 0, then the function is undefined, doesn't exist. If we have a radical sign or square root or any root, sometimes example of a square root of a negative even number, again, the function does not exist. So let's discuss the continuity of each of these functions. Here we have a polynomial function. So all these three functions will exist in any real numbers. So we take the first one. If we plot the graph, we get a parabola because the highest degree of s is 2. Our second graph is s is cubed, so we get 2 peaks. And when s is 4, we get 3 tenths. But our main concept here is that we can see from the interval any value negative infinity to positive infinity, all the three functions, they are all continuity. There's no discontinuity. There's no any broken points or holes or jumping or gaps. So as we said, polynomial functions is always continuity or continuous in any real numbers. And also polynomial functions are one of the most important types of functions used in calculus. We should be sure to understand the example, the previous example. As we see, polynomial functions is continuous on entire real number line. It doesn't have no holes, no jumps, or no gaps. But rational function, on the other hand, may have some continuities and some may be discontinuity. So that's the next example 2. We say f at s equal to 1 over x. When s equal to 0, the function is undefined. So that will be our discontinuity. The second question, when s is 1, the function is undefined. That will be our continuity. But the third, 1 over s squared plus 1. If s is 1, we get 2. If s is negative 1, we still get positive 1. We get 2. So the third is a rational function, but it's continuity in any real numbers from negative infinity to positive infinity. So let's see each of these solutions. The first one, this is the graph we get, 1 over x. And then the second, this is the graph, there's a discontinuity. Then the third, continuity throughout. So consider an open interval I that contains a real number c. If a function f is defined on I, except possible at c, and f is not continuous at c, then we say f is said to have a discontinuity at c, since the function is not continuous at c, then you have discontinuity at c. Now, discontinuities fall into 2 categories. We have the removable and non-removable. So a discontinuity at c is called removable when f can be made continuous by appropriately defining or redefining f at c. So for example, 2b, it has a removable discontinuity at 1 and 2. So to remove the discontinuity, all we need to do is redefine the function so that f at 1 will give us 2. That's from the previous example. And the function 1 over x was also non-removable discontinuity at s equal to 0 because it's only 1 over s. And we cannot remove. S always is, when it's 0, there's discontinuity. Now, we discuss continuity on a closed interval. Here we say that if f be a defined on a closed interval, the closed interval a and b, if f is continuous on the open interval a and b, and we have a condition that the limit s approaches a from the right, f at s equal to f at a, and the limit f approaches b from the left, f at s equal to f at b, then we say f is continuous on the closed interval a and b. Moreover, f is continuous from the right at a and also continuous from the left at b. Similar definitions again can be made to cover continuity on intervals of the form open A to close B and close interval A to open interval B. So let's discuss the continuity of g at x, 5 minus x, when s is greater than or equal to -1 and less than or equal to 2. Also s squared minus 1 when s is greater than 2 but is less than or equal to 3. Here, this case, we have two polynomial functions, 5 minus x and s squared minus 1, but they are continuous in the interval -1 to 2 and also from 2 to 3, respectively. So to conclude that g is continuous on the entire interval from -1 to 3, that is from -1 to 3, if these two functions are continuous, we need only to check the behavior of g when s equal to 2. So we're going to take the limit at g at x when s approaches 2 from left, and also g at s when s approaches 2 from right. When s approaches 2 from right, it will be s squared minus 1. From left, it will be 5 minus x. So when we solve these two, we find out that the answer is the same. So from left and from right, we have the same answer. That means there's no blocking point or there's no gap. So here we can say that the function, first of all, the limit of the function exists, and there's a continuity between the gap -1 to 3. So this is the graph. You can see there's a continuity all the way from -1 to +3. So again, that will be the conclusion of our lectures. In these lectures, again, we discuss about continuity in functions. And the main rule we should know is that when a function is continuous at a point, at any specific point, it means there's no interruption on the graph. If it's discontinuity, then there will be an interruption, either a hole or a gap, etc. So again, wish everybody the best and thank you for your time.